Good afternoon. My presentation is on the evolution of infinity. Anaximander of Miletus is a Greek philosopher who's credited for developing the concept of infinity. He used the word apeiron to describe it, which was the, quote, primal substance of which all things are made. Apeiron to him was unlimited, indefinite, or indeterminate in kind or quality, and he believed the world was generated through a seed which issues from the boundless. Pythagoras and his followers hated the idea of apeiron. To Pythagoras, apeiron was, quote, senseless, chaotic, indeterminate, and without structure. Pythagoras believed that the beauty of the world stemmed from planting the seed of the Paris, which is the limit, into the void of apeiron. Everything would change with the notion of infinity with a paradox of Zeno of Elea. He was a Greek philosopher, and he had one particular paradox that really confounded many mathematicians and scholars of that day. It was known as the dichotomy, which stated, quote, before you travel a distance from A to B, you must travel half that distance, and before you travel the half, you must travel a fourth, and before the fourth, an eighth, and so on without limit. That impact was tremendous. The increments became smaller and smaller to the point that people started questioning, how can an infinite number of finite runs, however small, ever be completed? Scholars thought that the traveler could never make it from A to B theoretically because it would take, the total time would be infinite. And as a result of this paradox, most mathematicians developed their, quote, repugnance of the idea of infinity. Well, Aristotle changed that a bit. He defined two types of infinity, the actual and the potential. Now, actual was not something he really bought into. To him, the actual was incomprehensible because, quote, the underlying process of such an actuality would require the whole of time. He did believe in the potential infinity, which were collections of open-ended infinities, since new items could be included at any time. Well, what does that mean? That means if you have integers and go up 1, 2, 3, 4, and they go toward infinity, you know later on it could be 100, 101, and 102, and later on it could be a million, 1,000,001, and 1,000,002. So they were approaching infinity, yet never truly at infinity. Now, his impact on contemporary mathematics, he basically let people know that there was no number, quote, infinity. He said, quote, we cannot conceive the entire set of natural numbers, but we can conceive the idea that every natural number, no matter how big, there is another. Well, Zeno's influence on infinity kept generations of mathematicians away from infinity. Those mathematicians believed that the universe was made up of finite numbers. Pythagoras, in fact, thought infinity was, quote, a negative concept. Since it could not be reached or described in finite terms, it was, to Pythagoras, quote, irrational. Well, Descartes also believed that the human mind was finite and limited. And he wrote, quote, I do not comprehend the infinite, for the nature of the infinite is such that it is not comprehended by a being such as I, who am finite. It would take until George Cantor's work in the latter half of the 19th century for mathematicians and scholars alike to even consider that actual infinity was acceptable. Galileo resurrected the mathematician's fascination for infinity through his paradox. And his paradox was as the following. He said, quote, are there more squares than roots, more roots than squares, or the same number of each? To him, infinities would be equal to each other because he believed, quote, the totality of all numbers is infinite and that the number of squares is infinite. Therefore, neither is the number of squares less than the totality of all numbers, nor the latter greater than the former. To Galileo, he concluded that, quote, the attributes equal, greater, and less are not applicable to the infinite, but only to finite qualities. John Wallis, he's the individual who developed the current symbol for infinity, which is the Leibniz skit. He modified the Roman numeral 1000, which was a C and then the I and the backward C for this new symbol. Prior to Wallis, they had the Ouroboros, was a symbol of a snake eating its own tail, which had represented infinity for decades. Now, Gottfried Wilhelm Leibniz believed that nature was infinite, but there was not an infinite number. So again, he believed that nature was infinite, but there was not an infinite number. He believed in the possibility of infinite being. To him it was, quote, unthinkable, both on philosophical and theological grounds, to deny that God is an infinite whole. George Cantor was a revolutionary man who basically created the foundation for actual infinity. Prior to Cantor, quote, infinity was not even considered a legitimate mathematical concept by most people. Now, Cantor developed a couple theories. One was the theory of transfinite numbers, numbers that are larger than finite numbers, but not necessarily infinite. And, quote, they provided access to the interior of God's infinite mind. He was the individual that developed this theory of sets, and it was wholly originally created. Therefore, many people to this day believe that Cantor was a mathematical genius, because he was the first mathematician to explore more than one type of infinity, and he focused on different types and sizes of infinity. He called the different sizes of infinity cardinalities and proved that two sets have the same size, or cardinality, when they can be put in a one-to-one correspondence with each other. He developed a set theory. And what he did is he showed that, quote, no matter what scheme is used to pair the real numbers with the natural numbers, it can be shown that some of the real numbers remain uncounted. Therefore, real numbers form a larger infinity than counting numbers, according to Cantor. And Cantor's findings were published in 1874, and he revealed that all real numbers, the set of all real numbers, was non-denumerable, which means uncountable infinite sets, providing the first examples of infinite sets with different magnitudes. Cantor was not pleased that Aristotle had pointed out that there was only a potential infinity but not an actual infinity, because according to Cantor, there was now definitively actual infinity. And Cantor condemned the centuries-old argument that was established by Aristotle, quote, on the grounds that it was fallacious to assume that infinite numbers must exhibit the same arithmetic characteristics as finite numbers. Cantor denounces absolute infinity deniers. He said, quote, all so-called proofs against the possibility of actual infinite numbers are faulty. From the outset, they expect or even impose all the properties of finite numbers upon the numbers in question, while on the other hand, the infinite numbers must constitute an entirely new kind of number whose nature is entirely dependent upon the nature of things and is an object of research, but not our arbitrariness or our prejudices. He had, again, countable infinities. Now, these would be countable because they would have the same one-to-one correspondence between them. So what did he do? He showed that the rational numbers and natural numbers have one-to-one correspondence. He proved that the, quote, infinite set of the even numbers would be put in one-to-one correspondence with all counting numbers. So you can see the countable infinities would be whole numbers, fractions, prime numbers. So he did that, and he created these sets, and we'll get into the notion that he called them Aleph sets. Cantor's uncountable infinities, well, those were such as interval of real numbers contain infinitely many numbers, and the reals have significantly more numbers than the rationals. So they were uncountable because they weren't in one-to-one correspondence. Cantor revealed that the set of real numbers was bigger than the set of rational numbers. He had hierarchies. He had tiers of infinity. And this was revolutionary. No one even before him even accepted actual infinity. And now he's creating these tiers, this hierarchy of infinities. So what he did, he had the higher orders and he had lower orders. Lower orders of infinity included integers and higher orders included real numbers. He had his theory of transfinite numbers. And he had a little bit of religious component to this, because to him the transfinite numbers, quote, provided access to the interior of God's infinite mind. And the transfinite numbers are numbers that are infinite in the sense that they are larger than all finite numbers, but not necessarily absolutely infinite. At this point, Cantor faced significant backlash. If you're going to be a revolutionary thinker, and you're going to cause a lot of backlash, and that's what happened. We had French mathematician Henri Poincaré regarded Cantor's set theory as, quote, a grave mathematical malady, a perverse pathological illness that would one day be cured. And also Leopold Kronecker, this was Cantor's former teacher and mentor, criticized Cantor and denounced the transfinite set theory. Now, Cantor was vulnerable to criticism. He was vulnerable because he cannot prove a continuum hypothesis. Now, the hypothesis was as follows. he was unable to prove that, quote, no infinite set of numbers with order between aleph null, which is a set of integers, and aleph 1, set of real numbers. So he could not really prove that there is no infinite set of numbers with order between a set of integers and a set of real numbers. The mounting criticism on him built and built and built, and his inability to, quote, determine the power of the continuum resulted in Cantor's being hospitalized for recurring cycles of manic depression. Cantor eventually was forced to take a break from math. He just had enough mentally. He couldn't deal with it. And he actually pulled away from math and started investigating philosophy and literature. He actually started trying to prove that Francis Bacon had written the works of Shakespeare. And that's an issue that exists today. That's a conspiracy theory that exists to this day. His inability to prove continuum hypothesis eventually resulted in his demise, and he would die physically and literally a broken man in the German sanatorium in 1918. Now, Cantor he's honored posthumously by David Hilbert. He described Cantor's transfinite numbers as, quote, the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. Now, to honor him, Hilbert created this paradox called Hilbert's Hotel in 1925. And this asks the following. If there were a hotel built with infinite rooms and each room was filled, how could the manager accommodate infinite incoming guests? Well, Hilbert's Hotel is actually a fascinating mathematical paradox, because you have your rooms numbered 1, 2, 3, 4, going on for infinity, right? And what happens here is that how would a manager place a newly arrived infinite number of guests into a hotel even though it's completely booked up? Well, Hilbert figured out a few solutions. One solution was to, quote, move the guests in room N to room 2N so that all even number of rooms are occupied. This leaves every other room, infinitely many, vacant and ready to accommodate the infinitely many people arriving. Well, he also used Euclid's theorem that there are, quote, infinitely many prime numbers to also locate the infinitely arriving guests. And what he would do is he would basically do this. He said we could move the current guest to the first prime number, 2, raise the number of their current room number. The incoming guest would be assigned rooms to the next prime number, 3, raised to distinct powers. And when more people arrived, they would be assigned rooms with prime number 5, raised to distinct powers. To this day, people continue to struggle with the concept of infinity. Children and adults alike tend to struggle with that concept because the real world is finite, and, quote, there are no real reference for discourse on the infinite. Since infinity is abstract, understanding is dependent on our, quote, ability to visualize it mentally. Now, psychologist Jean Piaget was one of the first psychologists to study children's understanding of infinity. And he concluded that in concrete operational stages of development, the child's ability to visualize the division of geometrical figure into smaller parts is limited to finite number of iterations, which means that the absolute infinity is very tricky. The actual infinity is very tricky, almost impossible for a child to understand, but potential infinity is something a child could understand. And there we go. The potential infinity is acquired by students at a much higher rate than actual infinity. Older students, they can grasp that, quote, the potential infinity is related to an ongoing process without end. For example, counting natural numbers. 1, 2, 3, 4. However, students struggle to conceive of the entire set of natural numbers at once as an actual infinity. Cantor's legacy. To this day, many students remain limited in their understanding of actual infinity by the fact that, quote, the infinite in mathematics is conceivable by means of finite tools. However, as students develop greater skills, they realize infinity cannot be perceived by the senses. It is revealed by reason. Through Cantor's set theory, George Cantor introduced a hierarchy of infinities that continue to fascinate and frustrate mathematicians to this day. Thank you.